Hello there, everyone, and welcome to this week's video, in which, well, I was thinking of what to do for this video, and I thought we might try and conquer something, which is probably going to be, I don't know, maybe, I think it's probably the biggest thing I've done, which is the Friedmann equations. So for those who don't know, the Friedmann equations basically govern the large-scale expansion, or contraction, maybe, of the universe. So Friedmann came up with them in 1922. Um, Funnily enough, they were independently rediscovered by this guy, Georges Lemaitre, in 1927. Um, they follow from the Einstein field equations, which we've already looked at. But basically, if you assume that the universe is homogeneous, so it's the same everywhere, and isotropic, which is the same in every direction, we get something called the cosmological principle. And assuming that, we can then derive the Friedmann equations, which govern the expansion of the universe. There's a strategy to this proof, so I don't know if I'll be able to get through the whole thing in one video because it's quite big. But essentially, we're going to try and write down this sort of general metric consistent with the cosmological principle, which we already know. It's called the FLRW metric. Then the painful bit, we've got to compute the geometric quantities which you need for the Einstein field equation. Wait, no, this is the easy bit. The painful bit is the energy momentum tensor for a perfect fluid, which is quite long, and then we can substitute it back into Einstein field equations. The Ricci scalar and Ricci tensor actually does take quite a bit of time, but it doesn't matter. I think we'll get right into it. What we're going to do is take a metric signature of minus, plus, 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 and then we're also going to be using natural units, so c is equal to 1, and we can restore that explicitly in the final equation. So let's begin by constructing the most general homogeneous isotropic metric. So a 3D space has constant curvature everywhere that's homogeneous and isotropic, so there are three possible geometries. We either have k is equal to +1, which is a spherical curvature, k is equal to 0, which is a Euclidean curvature, and k is equal to -1, which is hyperbolic. We have these three geometries that we can pick from. So the universe is expanding, so we want all spatial dimensions to be rescaled by a time-dependent factor, which we're going to call A. So A is going to be our scale factor here. And we have a metric for this, and the metric is the FLRW. It stands for Friedmann, Lemaitre, Robertson, Walker metric, which I definitely don't remember, and it was 100% written down in my notes, and I'm not going to pretend that I remembered that. Anyway, so we have that ds squared is equal to minus dt squared plus a squared t, remembering that a squared here is a function of t, being the scale factor, and then inside of our brackets, dr squared over 1 minus k r squared plus r squared d theta squared plus r squared sine squared theta d phi squared. And that is our FLRW metric. So what does everything mean here? Well, we have co-moving coordinates, so co-moving chords, which are, sorry, that was supposed to be DL, not DT. I remember something was wrong there. Shouldn't be any DT. So we have L, R, theta, and phi. So the R is dimensionless here. It's the factor of A of t with units of length carries the physical distance. so it's unitless. And AT encodes the entire expansion history of the universe. I guess that's to some extent self-explanatory. Observers at fixed r, theta, and phi are called co-moving observers, so they follow the average motion of the cosmic fluid and they don't have a particular velocity. So let's move on and look at components of the metric tensor. So we're here looking at G mu nu with mu nu being members of just 0, 1, 2, 3, which is of course just our L, R, theta, phi. So we have G O O is equal to -1, G11 is equal to a squared over 1 minus k r squared. G22 is equal to a squared r squared, and G33 is equal to a squared r squared sine squared theta. The metric is diagonal, so by the delta, the thingy delta. Its name has escaped me. The Kronecker delta. There we go. Oh, mind blank. So using our Kronecker delta, we can then find components of the inverses. So G00 then is equal to -1. G11 is equal to 1 minus k r squared over a squared. G22 is equal to 1 over a squared r squared, and G33 is equal to 1 over a squared r squared sine squared theta. 1, not r, sorry. We can find the determinant, which might be useful. The determinant of a diagonal matrix is just the product of its diagonal entries, so that we'll call G is the determinant of G mu nu, which is -1 times 1 minus k r squared a squared times a squared r squared times a squared r squared sine squared theta, which is just minus a squared r a to the 6, sorry, r to the 4 sine squared theta over 1 minus k r squared, and the thing that we care about, minus the root of minus g, is then equal to a cubed r squared sine theta over root 1 minus k r squared. Nice, that's useful. Next thing is Christoffel symbols that we need to deal with. So, I mean, I've done videos on the Christoffel symbols before, but they're defined purely in terms of this metric, so I don't even know if I should draw gamma like that. I'm probably just going to draw it like this for this video. Rho mu nu is equal to half g to the rho lambda. That's not a lambda. D mu g nu lambda plus d nu g mu lambda. Why do I keep doing that? Minus g lambda g, d lambda g mu nu. Nice. We have our diagonal metric, so G to the row lambda is equal to 0, where row does not equal to lambda. And this just collapses then into a single term. So we have that row mu nu is equal to half g to the row of d mu g nu row plus d nu g mu row plus minus d lambda d row g mu nu. Nice. I'm just gonna have time derivatives with the dot, like in mechanics. We only want symbols that will contribute to the 0, 0 and the 1, 1 components of the Ricci tensor. I'm not gonna compute all the non-zero ones. I don't think. No, I am just gonna do the 1, 1 and the 2, 2. So for the space, for the time space symbols, which is I and j and then 0, it's half g 0, 0 di gj 0 plus dj gi 0, which is half times minus 1 times 0 plus 0 minus g dot ij. I meant ij, not I0. This is simply half g dot ij. So for 1, 1, it's half g1, 1, g dot 1, 1 rather, which is half times 2a dots. Yeah, derivative of that, which would be 2a, derivative 1 over that, sorry, up here, 2a dots. Yeah, chain rule, cool. And that's just a dot over 1 minus k r squared. And then for the 2, 2 matrix, 2, 2, or did I even want that? No, I just wanted 0, 0, and 1, 1. Oh, great. 0, 0 is equal to 0. Useful. And for the time space symbols, we have that 0, j, and I. I don't think I'll. Sorry, I'm not even sure if I'm gonna need any more, because I'm just gonna need purely spatial ones, I think. No, I am. Yeah, because I'll need the ones to sum of a row. That's really annoying. I don't know if I'm going to write them all out because it is just a big waste of time, to be honest. And I've already done a video on how these work, so I think we need to talk that much about it. The only last thing that I want to mention on this is that we have the Hubble parameter h, which is a dot over a, and that's just a useful thing to remember. I'm not going to go through with derivations of the rest of them because I think that should be, again, I've already done a video. Ricci tensor. So it's obtained by contracting the first and the third indices of the Riemann tensor, of the Riemann tensor. So our mu nu, that's our Ricci, is here, mu nu rho, minus d nu rho mu rho plus why do I keep getting my lambdas wrong? Rho and then the one with rho lambda. Sorry, mu nu to the lambda minus mu lambda. Hardest thing about tensors is cycling through these and remembering which ones to do. Stupid indices. So there's high symmetry in the FLRW metric. So all of the off-diagonal components of the Ricci tensor with mu not equal to nu are just going to vanish because the metric is diagonal. So the cosmological principle forbids like perfect directions. Remember, we assuming homogeneous and we're assuming homogeneous and isotropic space, so it's kind of irrelevant. But now this really is quite a long one. We'll start off with 0, 0. So R0, 0 is equal to rho 0, 0 rho minus 0 rho plus rho lambda rho minus 0 lambda rho. Oh, I forgot the one there. Not lambda minus 0 lambda rho, and then this one should be 0 rho lambda. Yeah. Cool. Let's work out what all of these are. So term 1, there's no non-zero with lower indices, not. So that's just 0. The second term, the rho equals I is just going to give us the Hubble metric. So summing over all rho 1, 2, and 3, we're going to get that this is 3h. Yeah. Oh no, I need to take time derivative, don't I? So that's... We'll do this first. Time derivative of 3a dot over a is equal to 3a double dot a minus a dot squared, which is just 3 a double dot over a minus a dot squared over a squared. Yeah, that, because, yeah. So it's just 3 minus even, because I'm taking the minus, so minus d naught 3a dot over a is equal to minus 3a double dot over a plus 3a dot squared over a squared, which is 3h squared. Term 3, that's 0, so we can get rid of that. And term 4, this one takes slightly long. No, it doesn't. We'll do the same thing here, except we're doing a sum instead of a derivative. So we'll take sum over p lambda, rho lambda. So rho lambda rho 0 rho lambda. That's just minus. It has 1 to 3. I. That's minus 3. it's just going to be a dot over a squared. Yeah. Nice. Now we can assemble everything. So r naught naught is equal to minus 3a double dot over a 3a dot squared over a squared plus minus 3a dot over a squared squared. I actually put that in brackets and then minus, so add that. How do I get rid of it? What even is that? Okay. Stupid OneNote. That's minus 3a dot dot over a plus 3 dot squared over a squared minus 3 a dot squared over a squared. Cancel out. So r naught naught is equal to minus 3. Nice. So we can kind of look at what this might mean. So r naught naught is a measure of like local focusing of geodesics temporally. So it being negative accelerates, or for a double dot being greater than 0 then, or an accelerating expansion. What does that mean? Well, nearby like co-moving paths will converge. Co-moving being r theta and phi, all being constant. Yeah. Nice. Let's do R11. This is a bit of a terrible one. As in, it's a page of notes, and that's not even with everything. So I might miss bits, depending on how we're doing. But I think, I don't know, actually. I won't say anything too soon, because there really is quite a lot more maths to do. But I'm 23 minutes in, and we're about halfway done with the derivation. I think I can pick things up. I'm not going to go too much into detail on how we get R11, but essentially it's going to be this. Really struggling with the lambdas today. Right. Then this becomes things that we've already done. No, we haven't, but it's alright, because we're just taking derivatives of... No, we have. So it's going to be... So, I'm going to write out this. D... dt is equal to t. Yeah, I'm gonna go straight to the answer. And then r of 1, 1, 1 is gonna be k plus k squared r squared. And we get that from deriving that, and also that. Hope that explains. Then term 2. This one might be a bit of some. So we have this one row which is kr over 1 minus kr squared plus r plus 1 over r. Not 2, 1 over r. So the minus gr of that minus k plus k squared r squared over 1 minus kr squared plus 2 over r squared. Seems about right. Because I pulled, yeah, nice. Now term 3 is the, now it's term 4. So what we want for term 3 is that this is not equal to 0. And the two that satisfy that are 1, 1, 0 and 1, 1, 1. So lambda equals 0. We're going to have a contribution of 3a dot over a times squared a dot over 1 minus kr squared, which is just 3a dot squared over 1 minus kr squared. Yeah, that's right. Because yeah. And then for lambda equals 1, we're gonna have a contribution of kr. No, I'll do the bottom first one plus kr squared. Kr plus 2 over r times 1 minus kr squared kr. I think I'm safe to leave it like that. Now term 4. Term 4 just has a ton of terms. It's 7 that need to 0, 1, 0, 0. This is row lambda 0, 0, 0, 1, 1, 0, 1, 1, 2, 2, 3, 3, and 2, 1, I think. Yeah, that seems right, but 2, 1, 0, okay. So we will end up with a dot squared over 1 minus kr squared. That's minus that, minus a dot squared over 1 minus kr squared, minus k squared r squared over 1 minus kr squared, all squared. Minus 1 over r squared, minus 1 over r squared. And this is equal to 2a dot minus 2a dot 1 minus kr squared minus yeah. This is actually a fairly straightforward sum. I'm lying, it's just a lot of horrible algebra. So that gives us R11 as equal to k plus k squared r squared over 1 minus kr squared squared. That's our term 1 plus term 2, which is k plus k squared r squared over 1 minus kr squared squared plus 2 over r squared plus 1 minus kr squared over kr, and that's all squared. And this is the spatial part of term 3, which is going to be these bits and bobs, plus 2kr over 1 minus kr squared times 1 over r. Please let me have enough space. Plus minus kr squared, all of that squared, and over the top is k squared r squared minus 2 over r squared. Yay! Now we can simplify this down. This is 2 over r squared plus k squared, r squared over 1 minus kr squared all squared, plus 1 minus kr squared, 2k over that, minus 1 minus kr squared, r squared, minus 2 over r squared. So cancel, 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 which is 2k over 1 minus kr squared. And then the time-dependent bits are entirely separate, and that's not so bad. It's simply, I should probably have written plus time. I'm just going to get rid of the R11 and then that will solve my issue. So if I draw like a dotted line in there to show that this is that, and then the time dependent parts are a dot squared plus a double dots over 1 minus kr squared plus a dot squared over 1 minus kr squared minus 2a dot squared over 1 minus kr squared, and this is equal to a double dots plus 2a dot squared over 1 minus kr squared. So then we just sum those two and they're both over 1 minus kr squared, so R11 is equal to a double dot plus 2a dot squared plus 2k over 1 minus kr squared. Nice. I'm not doing the 2, 2 and 3, 3 components. You just do the same thing. R22 is equal to a double dot plus 2a dot squared plus 2k, and R33 is equal, that's not a 3, a double dot plus 2a dot squared plus 2k sine squared. You can probably see how all of this comes in from our metric. Here, different bits of the metric doing things as we increase the indices pair. So we have our 4. Now we do the Ritchie scalar, which is the bit where we contract using g to the mu nu. How are we doing for time? 34. Alright, I think I'm gonna get up to the end of the Einstein tensor, and then I think I'll be done with heavy tensor stuff and setup. Oh, I might need to do energy momentum tensor for a perfect field as well. Okay, I'll do that, then we'll be in a good place. So, the Ritchie scalar is g to the mu nu r to the mu nu, which is g00 r00 plus g11 r11 plus g22 r22 plus g33 r33. We've done a lot of the heavy lifting for this now, so g00 r00 is equal to minus 1 times minus 3 a double dot over a, which is 3 a double dot over a. G11 r11 is equal to 1 minus kr squared over a squared times a double dot plus 2a dot squared plus 2k over 1 minus kr squared. And this is a double dot plus 2a dot squared plus 2k over a squared. Yeah. And then G22R22 is equal to over A squared R squared. A double dot plus 2A dot plus 2 R squared, which is A double dot plus 2A dot squared plus 2K over A squared. Oh. Crazy. Not sure why I've written weight. Okay. G33 R33. Again, we already have that A squared R squared sine squared theta from our metric. So A double dot plus 2A squared 2K A dot squared, sorry, sine squared theta. I'm not going to do that, and then we just get am I leaving it like that? I can cancel out the sine squared theta, so that's A double dot plus 2A 2K over A squared R squared. So no, that R squared shouldn't be there. Oh, it doesn't really matter. No, I am gonna actually expand this. Leave it like that, just for the sake of equations. So we'll take this variable A. Is that a blemish on my screen or a? No, it was a blemish in this. I'll take A to be A double dot plus 2A dot squared plus 2K. So we get that the scalar is 3A plus A over A squared plus, yeah, I knew that shouldn't have been there, but it should, because then I'm going to put it in afterwards anyway, so it's actually just over A squared plus A over, yeah, because I can cancel those out, okay. Sorry, notes are confusing me. It should be R squared, so that's what was confused, because then these are all the same, okay. Which is 3A double dot over A plus 3A, I wanted that, 3A over A squared. Expanding and throwing that back in, that's 3A double dot over A plus 3 double dot over A plus 6 dot squared over A squared plus 6 K over A squared. And those sums, so it's just going to be 6 A double dot over A plus A dot squared over A squared plus K over A squared. Yeah. Einstein tensor is next. Yeah, we can finish this. So we know our Ritchie scalar. We know that this is all just building up to the next thing. So now we have the Einstein tensor G mu nu, which is R mu nu minus half little g mu nu r. Again, we've been through this different video. We're just going to do GOO and GO11. So GOO is equal to ROO minus 1 over 2 GOOR, which is minus 3A double dot over A minus half times minus 1 times 6A double dot over A plus A squared over A dot squared over A squared plus K over A squared. This is minus 3A double dot over A plus 3A plus 3 a dot over a squared plus 3k over a squared, which nicely cancels out. We get 3a dot plus k. I combine them there because there's no extra term. G11, what could it be? R11 minus half G11R. This is a double dot plus 2a dot squared. Okay, this is engraved into my memory permanently. I've written out so many times now. I love that you can do that in one note, it's really cool. 1 minus kr squared minus half times a squared over 1 minus kr squared times 6 a double dot over a plus a dot squared over a squared plus k over a squared. I could expand the second term, but I'm gonna just write the expanded thing down because it's quite tiresome to expand. So this then becomes a double dot plus 2a dot squared, and I would definitely make a mistake doing this. A double dot minus 3. This is just elementary algebra in terms of an expansion. That should cancel. Minus 2a double dot minus a dot squared minus k over 1 minus kr squared, which is RG11. I can actually just pull the minus in front, which I forgot to do, which is kind of the important thing. 2a double dot minus plus a squared plus k minus kr squared. Nice. So what does this bring us to? The energy momentum tensor, and we have our G11 and our G22, and right, let's do the energy momentum tensor. So this is a bit more wordy than righty. On sort of these large cosmological scales, the universe can be modelled as a perfect fluid, so it has no viscosity and no heat conduction. In the rest frame of that fluid, the energy momentum tensor takes this simple form, which is T mu nu being equal to P rho plus P u to the mu u to the nu plus P g to the mu nu. Rho is energy density, P is pressure, and u to the mu is just the full velocity of the fluid. I've done Navier-Stokes. You may remember bits for this from Navier-Stokes. If you've seen that video. For a co-moving fluid, which is at rest in our coordinates, the full velocity is purely in the time direction, so the normalization condition, which is g mu, I'm going to write it in so that I don't forget, mu is equal to -1. This then gives that g o u to 0 squared is equal to -1. So that's equal to -1, so u to the 0 equals 1. So u to the mu equals 1, 0, 0, 0. And then we ought to lower it as well, so we can do that. So T mu nu is equal to G mu alpha G nu beta T to the alpha beta. And we can see its components here. So T naught naught is equal to rho. T11 is equal to PA squared over 1 minus KR, my best friend. T22 is equal to PG22. Actually, I'm not going to write that bit because it's obvious. Which is, I forgot how to write, PA squared R squared. And T33 is equal to PG33. Again, why did I write that? PA squared R squared sine squared theta. Now that's really useful because This is just our right at the beginning of everything. It's just these guys, but a bit different. Lots of similarities. It's quite useful. Makes some of the algebra easier. T naught naught being equal to rho is just energy density measured by a co-moving observer. Pressure P sources spatial components, and it's important in determining whether the expansion is accelerating or decelerating. But it's been 46 minutes, probably not that long for you. I was interrupted, so it's been 46 minutes. And I don't know how much longer I can go on. So we have left next week to actually derive the equations and then find the continuity equation as well. But yeah, I've done fluid mechanics. I've done fluid mechanics with electrodynamics. I've done fluid mechanics with I've done general relativity, and now I'm doing fluid mechanics with general relativity, and it's really quite fun. So I hope you also found it funny. Fun, not funny. I hope you didn't find it funny. That would be a bit disturbing. I hope you found it enjoyable, and I will see you next week for part 2 of deriving the Friedmann equations, where we actually derive the Friedmann equations.